So one last example here. This is from a released free response test, and this time we have an area between curves problem that is calculator acting. So let's see the differences here. So I'm going to see what my plan is. So I want to integrate with respect to x, or I want to integrate with respect to y. Can I tell what my limits are going to be? The two functions I've been given, they're functions of x, so it's less work if I can integrate with respect to x, maybe, because at least I won't have to change these functions. So I'm going to trace along the bottom boundary of curve. That was pretty easy. I was tracing along the curve y equals 0 the whole time. I think here it's pretty clear from the picture that the left hand limit is x equals 1. The right hand limit is x equals 5. And you could just confirm those. You know that we can tell. This is the natural log curve. That's the linear curve. What are the x-intercepts of each of those curves? So the x-intercept of the natural log function, this is why I make you know your function booklet, is x equals 1. So that makes sense here. And the x limit, the x-intercept of the function 5 minus x is in fact 5, so those make sense. My bottom boundary is all the same, but watch what happens when I try to trace the top boundary. I'm tracing, I'm tracing along natural log. All of a sudden, my boundary turns, and I start tracing along this curve, y equals 5 minus x. So this is a lot like example 2. The one we did two different ways in your textbook. So we have a couple of options. We can split up this area into 2 separate regions. And for me, the top curve changed right here, where natural log of x and 5 minus x intersected. Do you know the intersection of the graph of y equals natural log of x and y equals 5 minus x off the top of your head? No, you don't. You might think that you could read it from this graph, but you don't know what it is. You could guess a number and then try to check it, but you're not going to guess this one off the top of your head. So we're going to use our calculator to find the x-coordinate of the place where these 2 graphs intersect. Let's just draw out our plan. So if I could figure out what that x value is, I'm going to imagine splitting this up into 2 regions. I'm going to call this region, I don't know, P over here and Q over here, just to have something to refer to them by. Now for region P, the upper limit is always, or the upper boundary is always natural log of x. The lower boundary is always y equals 0. For Q, the upper bound is always 5 minus x. The lower bound is always y equals 0. So I'm going to write 2 integrals, the integral from 1 to whatever this x value is. That'll give me the area of P. And I'm going to add to it the integral from x, whatever this x value is, to 5 to give me the area of Q. All right, so on your calculator, we're going to try to find the x-coordinate of the intersection of the graph of natural log of x and 5 minus x. So this is the equation we're trying to solve, and hopefully this will drive home to you the fact that we don't know how to solve this equation off the top of our head. So you're going to come to your calculator, you're going to graph the function y equals natural log of x. You're going to graph the function y equals 5 minus x. Let's see. Can I show you that on my calculator? Can I turn that? There we go. So that's y equals natural log of x, y equals 5 minus x. I'm going to graph that. I should get a graph like the one in the picture, and I do. So I'm looking for the x-coordinate of that point right there. That's the intersection of the 2 graphs. So I'm going to use the second and calc function and choose intersect. What happens is it asks me for the first curve, and it finds it pretty well on its own. So I'm going to say yes. Whoops. What I meant was, there we go. First curve, say yes. Second curve, say yes. It's like, should I guess what it is? Yes, please guess what it is. And your calculator can find the intersection. So I noticed that the x-coordinate of the intersection is 3.69344. That's really good, and you could write that down. I highly recommend you write it down. But you might also like to know that if you hit enter one more time, that little intersection sign goes away. And now I'm going to hit the store button. It's STO on my calculator. The graph goes away, and it says, oh, I should take the answer, which is the x-coordinate we just got, the x-coordinate of the intersection, and I'm going to have it, I'm going to pick a variable. I'm going to use capital letter A. So I'm going to use the alpha function, the alpha key, and I'm going to choose the letter A. It's a little green letter. Feel free to use any letter you like. And now that tells me that 3.69344 is stored in the variable A. So if I use the alpha and A and hit enter, that variable has a value. Try again. So alpha and A, followed by enter. The calculator thinks that capital A is equal to 3.69333, and that can save you some typing, which can sometimes save you an accidental error. So let's go back to here. All right, I have solved natural log of x equals 5 minus x. I got that the coordinate of the x-coordinate of the intersection is 3.69344. You could write that out, but you might find it convenient to write a little statement like let a equal 3.693. I'm going to integrate from 1 to a of natural log of x because the natural log function is on top and y equals 0 on bottom. And for that, what did I call it? Area P. And then I'm going to integrate from a to 5 of 5 minus x to get the area of Q. I'm going to add the two together and I get 2.985. Now you might also have noticed that we could have written one single integral for this area if we had thought about integrating with respect to y. If I integrate with respect to y, I'm taking rectangles that are horizontally oriented. I find the distance across that rectangle by subtracting x coordinates. Do I always have the same function on the right-hand side? Yeah. The right endpoint of those rectangles is always along that function, which we know is y equals 5 minus x. The rightmost coordinate of that rectangle is always going to be along this function, y equals natural log of x. And I can do what we did in that other example from your textbook, which is rewrite my boundary curves as functions of y and integrate from bottom to top of right minus left. That's what I'm going to do here. I'm going to take my two functions. I'm going to take y equals natural log of x. I'm going to solve that equation for x by exponentiating both sides. So I get x equals e to the y. I can take my other equation, y equals 5 minus x, and try to isolate the x. I get x equals 5 minus y. I'm still going to have to use my calculator to figure out the y coordinate now of that point of intersection, because that's going to be, I'm supposed to integrate from bottom to top. Well, the lowest down y in that picture is clearly y equals 0, but what's the highest up y? It's that y coordinate of the place where the two graphs intersect. So I can use my calculator the same way I did and find that I'm just going to call it capital B is equal to 1.30655. So I could have instead, I don't have to do this both ways, but I want to show you both ways. I could have written one integral, the integral from 0 to b of, so that's the integral from bottom to top of right minus left. That's 5 minus y minus e to the y. Again, this is a calculator active section, so there's no need to stop and try to figure out an antiderivative. We're going to evaluate this on your calculator. And look, we do get the same answer we got before. Either method is totally appropriate. We get the same answer, 2.985, either way. And I've got one more part here. Part C says the horizontal line y equals k divides R into two regions of equal area. Write but do not solve an equation involving one or more integrals whose solution gives the value of k. it's totally normal the first time you read this to think, oh my God, there's no way I'm going to be able to solve for k. It doesn't matter. It's going to feel very strange to write an equation that you don't know how to solve, but really all they're saying is that you should write any correct equation that contains the variable k, even though you don't know how to solve it. If it could be solved, its solution would give k. So write any correct equation that contains k. So I'm going to sketch in this line. I'm going to say that's the line y equals k. Now, k has divided R into two regions of equal area if the region above the line has an area that's equal to the region below the line. So just for discussion, I'm going to call this area H for high and this area L for low. If I can write an equation that just states that those two areas are equal to each other and it involves the letter K at all, I'll be finished with this problem. So that's exactly what I'm going to do. Notice here, this problem's here to kind of force you to prove that you can integrate with respect to y. Part A we could have done by integrating with respect to x, as long as we split up this area in the region R into two separate areas. Here there's no way to get this answer except by integrating with respect to y. So notice that really what I'm going to write is area L equals area H. So I'm going to need to write an integral expression for the area of L. I'm going to integrate from bottom to top of right minus left. And that's going to equal area H. Again, I'm going to integrate from bottom to top of right minus left. The bottommost y is 0. The uppermost y of region L is whatever this k value is. So it's going to be the upper limit on my first integral, and then I'm going to integrate from k to, remember what we called that y value b. So here's my integral. So in the picture I called this area L for low and this area H for high. So I'm integrating from 0 to k, from bottom to top of right minus left. And that's equal to the area of H. I'm going to integrate from bottom to top, k to b, of right minus